Hello, welcome to Prep for Analog Applications and Design Roles. One question you may receive is, how do certain measurements work? So, for instance, how does oscilloscope work? Well, it turns out when we use an oscilloscope to probe our circuit, that this outside pin is ground, B and C, for instance, and then inside the oscilloscope is an ADC, analog to digital converter, and it's sampling the voltages here and converting those into what you see on your screen. And it's just doing that directly. There are very fancy ADC things you can do here. You can do what's called interleaving, which is where you take multiple ADCs and if one of them samples here in time, S1, the next one will sample here, S2, the next one will sample here, S3, and then the first one comes back around, S1. If you had only one ADC, then the sampling period would be this long, T S1. But now that you have an interleaved ADC, now your sampling period is only this long, T S1, 2. And you make this the same length of time, and you make this the same length as well. And now with 3 ADCs, you end up with a TS equal to 1 over N, the number of ADCs you're interleaving, times the S of 1 ADC. So this is a great way to get faster sampling out of different ADCs. And this is how your oscilloscope keeps up with the electronics you're trying to sample. Another measurement device you may work with is another box. In this case, this box is a spectrum analyzer. And this one, instead of doing in time like the oscilloscope does, this one is frequency. And so start the lowest frequency here and go to the highest frequency here. And that means that this point here is some spectrum of, again, a sampled waveform. This is here. Then how does it make such better measurements of the spectrum than our oscilloscope does otherwise in time? So the way it does it is it takes the signal and it down converts it. So there's a mixer in here. Which takes the frequency that we want to care about. We care about this signal here, F care. And all that information is traveling super fast over here. This is, again, frequency domain. But we only have an ADC that can do a good job down here. And so we want to make it to where the ADC can do its good job. So what we do is we move all this information down here. And that's done by doing multiplication. So we have this information here, and then we have something like a mixer signal we can do here. And by multiplying these together, we're able to shift. This is the F center. This is the F of the local oscillator. Then we get to move this over here. And that's going to be F nu, where F nu is equal to the center frequency minus the local oscillator frequency that you're mixing with your signal. That's how you're able to make good measurements with the ADC that's this slow on signals that are as fast as the center here, the F car. All right, on the simpler note, how does a multimeter make its measurements? All right, so you have I probe here and V probe here. And then this is common ground here. And so it turns out that this node here uses another ADC. So here's ground again, and here's V. And so it's measuring the voltage here. And that's how you get a reading here. And then what if, instead of a voltage, it's a resistor that you're time between those two? How does it do that then? Well, then it's applying a small voltage actually. So there's a little voltage source here. And there's a little resistor here. I guess that's the best way to do it. So we'll take that here. And then the ADC is able to measure the I drop across this. So there's some voltage drop here. The drop from the I, and it will measure that drop versus this resistor. And it will calculate our M based off of a voltage divider. So our M equals the ratio of the measurement and R drop, or V drop. Okay. And then current is made the same way. So this is actually a current measurement. And really, this device is doing the same thing on this side as well. It's just not applying the voltage this time. All right, hope that was helpful.